right, welcome back once again, my natural disaster students. Next topic we're going to look at are floods. Floods are important for us to understand because basically floods happen everywhere. Virtually every continent gets floods. Not every place has devastating earthquakes or volcanoes or are affected directly by tsunamis, but every place has floods. And so they are, from that perspective, the most widespread of our disaster types, and annually some of the worst and most devastating ones that we have. So, first off, basic cause of floods, too much water. Now, as simple and silly as that statement is, it's really true. The basic cause of floods is too much water. Now, we want to get a little more scientific than that, obviously. The way we're going to think about this is input versus output. So the amount of water going into a river versus how much that river can take water out. So if you have more water coming into a river than the river can take out, you have too much water, you're going to have a flood. So that's how we're really going to look at this. So yes, too much water is the basic cause, but the core of it really is you have more water coming in than you can get out. So your input is greater than your output. And that's what really drives these. Now, if we're going to talk about input and output, we need a way to measure input and output. And we do that with what's called discharge. Discharge is the amount of water flowing in a river or stream. And just as a side note, river, stream, creek, really no difference between those three terms. Traditionally, river is bigger, stream is smaller, creek is smaller than that. But there's no numeric threshold for either one of those. So I will use the terms river, stream, and creek interchangeably, and that's okay. So discharge, the amount of water flowing in a river or stream. How do we measure that? It's the cross-sectional area times the velocity. So if this represents a river, and the gray part represents the bottom of the river, the purple is the cross-sectional area. So if we can measure this and multiply it by the velocity, we will get discharge. And the units that we get are cubic feet per second. So basically a cube that's 1 foot by 1 foot by 1 foot, filled with water. How many of those going by every second? If it's a metric country, we might do it in cubic meters, but same thing, it's a cube that's 1 meter by 1 meter by 1 meter. And again, how many of those flying by every second filled with water? 5, 100, 1,000, 10,000, just depends on the size of the river. But if we're going to measure, or I should say, if we're going to talk about floods being input greater than output, then we have to have a way to measure that input and output. And we do that with discharge. So that's why discharge ends up being very important for us. All right, let me just jump ahead here to number 9. I do want to mention quickly, we have different types of channels to rivers. So the shape of the river itself can vary quite a bit. One type of river channel is what we call a meandering river, and it swings back and forth quite a bit. It looks like a snake. It just goes left and right, left and right. And we have in those features what we call point bars and cut banks. A point bar is on the inside of one of these turns. Inside of one of these turns. And the cut bank is on the outside of the turn. So the point bar on the inside is an area of deposition. We're depositing material there. The outside, the cut bank, is an area of erosion. We're removing material from that part of our river stream. So I would not build anywhere near a meandering river, but if you had to, building near the cut bank is a very dangerous place because this is actively eroding and moving and changing its position, and will eventually undercut whatever building you build here. So don't build near meandering rivers, but if you do not build near the cut bank. That's definitely the worst place to be along a meandering river. Now, if a meandering river meanders enough, it can actually cut back on itself. And when it does that, it creates a meander cutoff. And so that's where a meander like this grows and grows, and you get this little neck here that gets narrower and narrower, and eventually you pinch that off, and the river continues along its normal path, and you leave behind the old meander here, which we call an oxbow lake. And it just gives you an idea just how dynamic these river channels can be, how much they can swing around over a period of years. And so building anywhere in these rivers like this is, again, a risky proposition. You can easily find your building being destroyed quite easily. All right, let's quickly get into then our different types of floods. There's two main types of floods that I'm going to talk about in class. First one is what we call a flash flood. Called flash flood because they're quick, so the water rises up quick, but it also tends to go back down quick. These are usually the result of a lot of water coming in a short period of time, so usually like a thunderstorm or a series of thunderstorms that can cause these. The other type of flood that we have is what's called a regional flood. This is sort of the opposite. It typically occurs over a bigger area, but over a longer period of time. And as a result of typically heavy rain, but over a bigger area, but not quite the super intense rain you get with a flash flood. So the water rises up maybe over a period of days or even weeks, in some cases even months. And then it takes correspondingly, again, days or weeks or months for that water to go back down. So a much slower process, but still very damaging. Between the two of these, both are very damaging. Flash floods can be more deadly, again, because of the speed with which they occur. Regional floods typically are slower to rise up. That gives us, as people, more time to react and get out of the way. Don't get me wrong, I'm not saying people don't die in regional floods. They do, unfortunately. But everything else being equal, you'd expect more fatalities from a flash flood than a regional flood. Again, because of the speed with which it occurs. Quickly talk about the effects humans have on floods, particularly urbanization, so building big cities in and around areas with floods. What we tend to do when we build infrastructure, again, roads, parking lots, buildings, things like that, we tend to increase the amount of water that gets into our rivers. And as a result, you have more input into a river than you would if it was a natural environment. And so if you're right near that balance of input versus output, but suddenly you have a lot of urban area, a big city nearby, you're going to put a lot more water into that river. And typically much more quickly tilt that balance of input and output towards flood. So too much input versus output. So that's what building cities along rivers tends to do. We do tend to make the flood events actually worse. All right, now, humans have been dealing with floods since humans have been humans. And typically we don't just sit around and not try to do anything. We try to respond to these. If we go back to that initial idea of input versus output, we want to try to alter that balance somehow. Well, ultimately, in terms of input control, we can't stop the rain. Despite many efforts over many years, we cannot control the rain. But what we can do is build dams. And dams are very good at controlling the water in the river. Again, you're not controlling the water coming out of the sky, but you are controlling it once it's on the ground, in essence. And so it does a pretty good job of controlling that water in the river. And so in essence, if you can control the water in the river, you can control the output of the dam, which then is the input for all the cities downstream of it. So dams are quite good at that. Dams, however, are very expensive. There are negative environmental impacts from dams as well beyond that. But they do a very good job, for the most part, of controlling flooding. And we built a lot of dams around the world. Virtually every major river in the U.S. at this point is pretty much built out as far as dams are concerned to control flooding. So flooding along our major rivers these days is not nearly as much of a problem as it was, say, 80, 100 years ago, because we built so many of these dams. All right, next up. Let's see, so that's our input control. Output, if we start looking at output, we can build channels. When we build channels, what we tend to do is we tend to line our channels with concrete, and that makes the water flow faster. Going back to our definition of discharge, which involves velocity, if you increase velocity, you increase discharge, and that allows the river to carry more water. So it restores that output balance to our input and output. Levees, basically what they do is they make a bigger channel with which to have the water flowing. Again, you increase your cross-sectional area, which increases your discharge, which is good. You want to have a bigger discharge capability. So that's what levees tend to do. So as far as trying to control the output, channelization and levees are two of the big ways that we do that. And generally, they're fairly successful at controlling flooding when we do that. All right. A couple other examples in the presentation as well that I won't get to, but make sure you go through and look at those. Are some of our case studies for floods. We have a flash flood example as well as a regional flood example in your example. So, all right, so that's flood. Hopefully I have not flooded you with too much information. I know. But part of you is laughing. It is. Anyway, any questions, let me know. Otherwise, I'll see you guys next time. Thanks.